Topic is inherited DOC2 deficiency in patients with early onset invasive infections. In the introduction, we have the combined immunodeficiencies comprise a heterogeneous group of inherited defects of the immune system that are characterized by quantitative and qualitative defects of T lymphocytes. These defects are associated with primary or secondary defects of B lymphocytes. In patients with combined immunodeficiencies, impairment of adaptive immunity causes increased susceptibility to early onset. Severe infections with a variety of viruses, bacteria, fungi, and parasites. Identification of the gene defects that cause combined immunodeficiencies has helped patients considerably, provided new and important insights into mechanisms governing T cells development and functions in humans, and led to an understanding of the molecular and cellular basis of the common conditions, including the autoimmunity, allergy, inflammation, and cancer. Next generation sequences has revolutionized a study of the human genetic disease, enabling the identification of the new causative genetic variations in an increasing number of patients with primary immunodeficiencies. Here we will report on human dedicator of cytokinesis 2, that is the DOC2 deficiency as a combined immunodeficiency in 5 unrelated patients of various ethnic origins. These patients present a distinctive clinical phenotype of early onset, invasive infections that were associated with a broad spectrum of defects in hematopoietic and non-hematopoietic immunity.
Like any rather complicated machine, and the immune system consists of quite a lot of different cells and molecules, and they have to interact in various ways, things can go wrong sometimes in the immune response, and you can end up with immunodeficiency, a deficient immune response. Sometimes this is due to external agents, and in that case we refer to secondary immunodeficiency. But now we're going to discuss primary immunodeficiency. So primary immunodeficiency is defective immunity that is due to either an inherited or an acquired gene defect. The distribution of cellular primary immunodeficiency defects is that around about half of them are caused by defects in B cells and therefore in antibody production. Around about 20% of primary immunodeficiency defects are combined T and B cell defects. Approximately 20% affect the phagocytic cells. And around about 10% affect just the T cells without affecting other parts of the immune response. The consequences of primary immunodeficiency are that we see opportunistic infections. These are infections that most of us, most of the time, are not really troubled by. We will deal with them perfectly adequately. But in patients with primary immunodeficiency, these infectious agents take the opportunity of the fact that there is a defective immune response to establish disease. The type of infections actually reflects the defect. So a defect in phagocytic cells will result in a different spectrum of infections to, for example, a defect in B lymphocytes. Immunodeficiency affecting T cells results in predominantly intracellular infections, for example, viruses, mycobacteria, and so forth. Whereas immunodeficiency affecting phagocytic cells and B cells and complement mainly results in extracellular bacteria. A little bit of background about primary immunodeficiency. Most primary immunodeficiencies are caused by an inherited gene defect. although, as already mentioned, some are due to spontaneous mutations. The inheritance may be autosomal recessive, in other words, both copies need to be detected, or autosomal dominance, where only one copy needs to be detected. Others are X-linked, and therefore more common in boys than girls. The severity will vary depending on the nature of the mutation. These diseases tend to manifest themselves in infancy. The vast majority of them are inherited gene defects. Therefore, you tend to pick them up in the early years of life. When infants are a few months or 1 or 2 years old, they'll keep getting recurrent infections, they'll be investigated for this, and in some of those individuals, they will be found to have a primary immunodeficiency. Most primary immunodeficiencies have a low prevalence. They're fairly rare diseases, generally speaking. However, the study of primary immunodeficiencies has provided valuable insights into individual components of the immune response. So although they're relatively uncommon, it's enabled us to answer questions about how the immune system functions, because we can identify individuals that have one particular component of the immune system that is dysfunctional due to these inherited gene defects. As already mentioned, quite a few primary immunodeficiencies are caused by genes that are present in the X chromosome, and therefore these diseases are more common in boys. And here's a list of some of the X-linked primary immunodeficiencies. And as you can see, there are a number of these. And we will be discussing some of these a little later in this lecture. Examples of primary immunodeficiencies that affect the innate response include complement deficiencies, paroxysmal nocturnal hemoglobinuria, hereditary angioedema, chronic granulomatous disease, myeloperoxidase deficiency, glucose 6-phosphate dehydrogenase deficiency, the leukocyte adhesion deficiency, Chedia-Higashi syndrome, and a number of autoinflammatory disorders.
In the application in medicine, we study that combined immunodeficiencies are marked by inborn errors of T cells immunity, in which the T cells are present quantitatively and functional deficiencies. Impaired humoral immunity is also common in patients that have a severe infection, autoimmunity, or both. The specific molecular, cellular, and clinical features of many types of combined immunodeficiencies remain unknown.
Every second of your life you are under attack. Billions of bacteria, viruses and fungi are trying to make you their home. So our bodies have developed a super complex little army of guards, soldiers, intelligence, weapons factories and communicators to protect you from, dying. For this video, let's assume the immune system has 12 different jobs. For example, kill enemies, communicate, etc. And it has 21 different cells and 2 protein forces. These cells have up to 4 different jobs. Let's assign them. Here are the interactions. Now, let's make this understandable. First of all, let's add colors to the jobs. Now, let's illustrate the cells. The central color represents the main job of the cell, while the surrounding ones represent secondary duties. Now the immune system looks like this. Now the interactions. Isn't this complexity just awesome? For this video we will only talk about these cells and ignore the rest. So what happens in the case of an infection? It's a beautiful day when suddenly a wild rusty nail appears and you cut yourself. The first barrier of the immune system is breached, your skin. Nearby bacteria seize on the opportunity and enter your wound. They start using up the body's resources and double their numbers about every 20 minutes. At first they fly under the radar, but when a certain bacterial population is reached, they change their behavior and start to damage around them. The immune system has to stop them as fast as possible. First of all, your guard cells, known as macrophages, intervene. They are huge cells that guard every border region of the body. Most of the time, they alone can suffocate an attack, because they can devour up to 100 intruders each. They swallow the intruder whole and trap it inside the membrane. Then the enemy gets broken down by enzymes and is killed. On top of that, they cause inflammation by ordering the blood vessels to release water into the battlefield, so fighting becomes easier. You notice this as a very mild swelling. When the macrophages fight for too long, they call in heavy backup by releasing messenger proteins that communicate location and urgency. Neutrophils leave their patrol routes in the blood and move to the battlefield. The neutrophils fight so furiously that they kill healthy cells in the process. On top of that, they generate barriers that trap and kill the bacteria. They are indeed so deadly that they evolved to commit suicide after 5 days to prevent them from causing too much damage. If this is not enough to stop the invasion, the brain of the immune system kicks in. The dendritic cell gets active. It reacts to the signals of the soldiers and starts collecting samples from the enemies. They rip them into pieces and present the parts on their outer layer. Now, the dendritic cell makes a crucial decision. Should they call for antivirus forces to eradicate infected body cells or an army of bacteria killers? In this case, antibacterial forces are necessary. It then travels to the closest lymph node in about a day. Here, billions of helper and killer T cells are waiting to be activated. When T cells are born, they go through a difficult and complicated training process, and only of course arrives. The surviving cells are equipped with a specific setup. And the dendritic cell is on its way looking for a helper T cell with a setup that's just right. It's looking for a helper T cell that can bind to the parts of the intruders which the dendritic cell has presented on its membrane. When it finally finds one, a chain reaction takes place. The helper T cell is activated. It quickly duplicates thousands of times. Some become memory T cells that stay in the lymph node and will make you practically immune against this enemy. Some travel to the field of battle to help out. And the third group goes on to travel to the center of the lymph node to activate a very powerful weapons factory. Like the T cells, they're born with a specific setup. And with a B cell and a T cell with the same set of needs, hell breaks loose. The B cell duplicates rapidly and starts producing millions of little weapons. They work so hard that they would literally die from exhaustion very fast. Here, helper T cells play another important role. They stimulate the hard-working factories and tell them, don't die yet, we still need you, keep going. This also ensures that the factories die if the infection is over, so the body doesn't waste energy or hurt itself. But what is produced by the B cells? You've heard of them, of course, antibodies. Little proteins that are engineered to bind to the surface of the specific intruder. There are even different kinds of antibodies that have slightly different.
In the method we have this video.
The adaptive immune system is elegantly choreographed to recognize and attack viruses and other pathogens that are foreign to the body. This animation will walk through how a critical component of the adaptive immune system, the T-cell receptor, or TCR, alerts the immune system to mount an attack through a cascading series of responses. First, let's take a look at how a virus infects the cell. A virus injects its genome into the host cell and commandeers the cell's internal machinery. Because the virus is inside the cell membrane seems to protect the virus from detection by the host. However, the human body has a strategy to survey even the inside of its own cells, an intricate mechanism in which cells decimate some of their own contents and display a sample of these contents on the outside of their cell membranes. This display is accomplished using a protein called the human leukocyte antigen, or HLA. HLA proteins cover the surface of cells, displaying samples of the proteins those cells contain, analogous to the barcode on the outside of packages at the grocery store. As part of the human immune system, T cells are designed to identify those HLA-displayed proteins that are not part of the normal cell, and therefore indicate the presence of a pathogen inside the cell. T cells circulate in the bloodstream, with proteins on their surface termed T cell receptors. These receptors interact with or scan the HLA-displayed proteins or barcodes looking for a match. The body is equipped with an immense number of T cells, each one displaying only one kind of T cell receptor.
In the methods, we have the performing genetic and cellular immunologic studies involving 5 unrelated children with early onset invasive bacterial and viral infections, lymphopenia and detective T cells, B cells, and natural killer cells response. 2 patients died early in childhood after allogenic hematopoietic stem cells transplantation. The other 3 have normalization of the T cell functions and clinical improvement.
Now let's talk about some important cytokines that you need to know for the boards, and we'll separate these by the cell that makes the cytokines. Let's start with macrophages. Macrophages produce IL-1, IL-6, IL-8, IL-12, as well as TNF-alpha. So let's talk about each of these individually. IL-1 is an endogenous pyrogen that causes fever and acute inflammation, general acute inflammation. It activates the endothelium, which will then start to...
In accord, the identified biallelic mutations in the indicator of the cytokinesis 2 gene in these 5 patients. RAC1 activation was impaired in the T cells shamanic-induced migration, and actin polymerization were defective in T cells, B cells, and NK cells. NK cells degranulation was also affected. Interferon A and interferon delta. Reduction by peripheral blood mononuclear cells was disseminated after viral infection. Moreover, in DOC2 deficient fibroblasts, viral replication was increased and viral-induced cell death was in changes. These conditions were normalized by treatment with interferon alpha-2b or after suppression of wild-type TYK2. In the conclusion, we have the autosomal recessive DOC2 deficiency is a new Mendelian disorder with pleiotropic defects of hematopoietic and non-hematopoietic immunity. Children with clinical feature of combining immunodeficiencies, especially with early onset invasive infection, may have this condition. Thank you.